Hi, so let's just review where we were last time. We introduced the electric potential and electric potential energy and voltages. So just remind you, the key equation was this, that the, uh, the electric potential energy of a charge Q is given by the product of the charge with the electric potential at the location of the charge. Now, if the charge is moving through a circuit, it moves from an initial point to a final point. We define delta V to be the electric potential at the final position minus the electric potential at the initial position. So this delta V multiplied by the charge that moves between those 2 points gives the change of electric potential energy of that charge. And everything here may be positive or negative. Everything. These equations apply to positive and negative charges, even though for now we focus on those positive fictitious charges. So our Q in that equation would be a positive number. So all the Q's in our equations would be positive. But delta V may be positive or negative, V may be positive or negative, U and delta U also may be positive or negative. Okay, let's do a very simple example of a question. You have a 12 volts battery. Remember, this is the voltage of the battery. What that 12 volt means is a delta V is a difference of potential, electric potential between the positive terminal and the negative terminal. Notice again this confusing double use of V. Here the V here is for the units volts, 12 volts. The V here is not a unit, is the electric potential, the difference of electric potential. So you see capital V is used for as a double duty, as a unit for volts and as meaning the electric potential. Now let's say this battery is connected to some circuit. I don't show the entire circuit, so there's some resistors connected, but you're told that there's a current of 3 amps flowing that way. Okay. Then first question: if you wait for 5 seconds, how much charge will go through the battery in 5 seconds? Now you know the current, you know I is delta Q over delta T. You can find how much charge goes through the battery. You just say delta Q equal I times delta T. So in 5 seconds, when the current is 3 amps, you get 15.0 Coulomb. Next question. Those charges, this amount of charge, as it goes through the battery, sees its potential energy, electric potential energy change. And this energy is supplied by the battery. So how much energy is supplied to the charges, to those 15 coulombs? So I'm still working with 5 seconds. How much energy is supplied to those 15 coulombs by the battery? Okay. So now we want a delta U. Okay. And delta U is just given by the charge times delta V. So the change of electric potential energy of the charges is equal to the charge that went through the battery, which here I call delta Q. In the previous equation, I called that just Q, but here we just use delta Q. That just represents the total amount of charge that went to the battery. So it's delta Q multiplied by delta V. Okay, now be careful. Delta V is always V final minus V initial. What do we mean by V final and V initial here? We're following the motion of the charges. So again, remember, we're focusing on the motion of those positive charges, fictitious charges. So they're moving in the direction of the current. So if you follow those charges, those positive charges, they move in that direction. They go from this side here, enter the battery, and then come out here. So this is, we use this point here as the initial point before they enter the battery, and here this is the final point. So V final is the electric potential here, which we don't know. Notice, remember, V is like Y. I don't know the value of V here, and I don't know the V here. But here I want V final minus V initial. So I want the V on this side after it went to the battery minus the V on this side. So because the V here we know is 12 volts above the V here, delta V is just 12 volts, okay, plus 12 volts, because we went from this side to this side. Okay, so the positive charges, to summarize, the positive charges move that way. As they move from this side to this side, the delta V they go through is plus 12 volts, because V final minus V initial is plus 12 volts. If we were moving in that direction from top to bottom, then delta V would be minus 12 volts. But here we're moving from that side to that side, delta V is plus 12 volts. So we take our delta Q, which was 15 coulombs, multiplied by 12 volts, and we get 180 joules, because it's an energy. Now, pay attention, that was a trick question. The energy supplied by the charge of the battery, to calculate this, we needed to use delta V here of the battery, which is 12 volts. It has 2 sig figs. So really here that was 15.0 coulomb multiplied by 12 volts. So my final answer must have 2 sig figs, because the delta V was at 2 sig figs. So the final answer with the correct number of sig figs should be 1.8 times 10 to the 2 joules. Okay, now we can ask a different question. What is the power produced by the battery? Again, a quick reminder about mechanics. How is power defined? The power produced by some source of energy is the work done by the source divided by how long it took to provide that work. Now, in principle, power can be positive or negative, because work can be positive or negative. Now, by convention here in circus, we're going to work only with positive powers. So remember, work is just is related to, in most cases, when forces are conservative, work is just a change of potential energy. So in our case, we can just replace work by the change of potential energy, but we want to work with positive power, so I'll take an absolute value. So the change of potential energy divided by delta T gives us the power, okay, in absolute value. So the units of power are joules per second, and joules per second is given a special name, it's called a watt. Now, what's the meaning of power? Why do we introduce this? Let's say that you're asked to do a certain task. Let's say you're asked to take 1,000 kilograms and move it up to the top of the bookshelves, which are, let's say, 2 meters tall. So you have to move 1,000 kilograms of things, let's say books or weights or whatever. 1,000 kilograms, you have to move them up by 2 meters. You can calculate the work that is required. That would just be mgh, the mass total mass times g times the height of your bookshelves. Now, you take 1,000 kilograms. If I'm asked to do that, I cannot do it in one step. So I can take, let's say, I can break down the 1,000 kilograms, let's say, in pieces of 10 kilograms each. And I can do that 100 times, 10 kilograms, 10 kilograms, and so on. I can do that, and I have done a certain amount of work, but it would have taken me quite a bit of time. Now, you take someone very strong, let's say the Incredible Hulk. He takes 1,000 kilograms and moves it just in 1 second, just in one step, everything at once. The work that I did by moving in steps of 10 kilograms and the work done by the Hulk is the same, because it's mgh. But obviously, I'm less powerful than the Hulk. And the difference is that I took quite a bit of time to do the task, and he did it very, very quickly in one step. So we did the same amount of work, but we exerted different power. The power we produce is very different. He is much more powerful than I am. So that's why we define power to be work divided by delta T. In the case of the Hulk, he did the same amount of work as I did, but in a very small delta T, so you get a large power. And my power was much smaller because my delta T was much longer. Okay, now let's go back to the question. What was the power produced by the battery? We said that it produced 180 joules. Now I go back to using the number with 3 sig figs, because I'm doing a step of the calculation. The battery produced 180 joules that was transferred to the charges in 5 seconds. So that's the change of potential energy of the charges divided by the time it took and that gives 36 watts. That's the power generated by the battery in our example. Okay, now let's go back to the definition. So power is the change of electric potential energy. We take the absolute value divided by delta T. Now remember, delta U electric, we said, is the amount of charge that, let's say I call delta Q here. I could call that Q or delta Q. It's just a total amount of charge. So delta U is the charge multiplied by delta V. Okay, and I put the absolute value here. Again, to be general here, I should put an absolute value here, but we work with positive charges, so I won't bother. So delta U is just delta Q times delta V. But now you recognize this ratio, delta V over delta T, okay? Oh, sorry. I focus on this side. Delta Q over delta T. This ratio here is the current. So this equation is just I times delta V. And that's the power produced by, let's say, a battery, okay, in absolute value. So that's the key equation. That's an important equation. Actually, we talked about the power produced by a battery, but you can apply that to resistors as well, okay. For a resistor, though, we have, in addition, delta V can be related to to the current and the resistance using Ohm's law. So this applies to batteries and resistors, but for resistors, we can replace delta V by IR. So that equation becomes P equal I times IR, which is Ri squared. So you get that the power in a resistor can be written as Ri squared. Okay, that's the same equation as this using Ohm's law. Using again Ohm's law, so here if you replace delta V by IR, you get Ri squared. But if you go here and replace using Ohm's law, you replace I by delta V over R, replace I by delta V over R, what do you get? You get delta V squared over R. So that's the other form here. So this form is for the power of batteries and resistors. These two forms are obviously valid only for resistors because you have a resistance there. But those are three equations for power. Okay, and those are important equations. Okay, so just a last comment. What is the meaning of power in an electrical circuit? So let's say you look at the power in a battery. The power means what? Is the amount of energy per second transferred to the electric charges that are moving through inside the battery. Now there's a warning here I must mention. For now, for a little while, our batteries will always be giving energy to the charges. But later, in a couple of weeks or so, we're going to talk about batteries that are actually taking energy from charges. So strictly speaking, for now, don't worry too much about that. For now, I should just mention the full rule. When I say that power P in a battery is energy transferred to the electric charges, this is true only when the current flows out of the positive terminal of a battery. Then the battery is giving energy to the charges. It turns out that in more complicated circuits, you can have cases where you have batteries in which the current enters a positive terminal instead of coming out of the positive terminal. Those batteries, the power will have a different meaning in those cases. But for now, in circuits where you have only one battery and just resistors, then you don't have to worry about this warning. We will always have current flowing out of the positive terminal, in which case energy is always given to the charges by the battery. Okay? So for now, ignore this comment here, and you can see that for now, the power is always energy transferred to the charges. In resistors, the power that we calculate is actually power or energy per second taken from the charges and given off, transformed into another form. So resistors, they transform energy carried by the charges into what form of energy? Usually it's heat, because resistors, they get hot when there's a current flowing through them. Where is this heat energy coming from? It's energy that is taken away from the charges. How much energy? How much energy per second is given by the power that we calculated before. So the resistors transform energy of the charges into heat, or sometimes into light. For example, if you have a light bulb, inside is really what is the source of light is really a small resistor that is so hot that it starts to radiate light, and the energy uh, that the energy in the light comes from electrical energy that were in the charges. Okay, so batteries give energy to the charges, and a resistor take energy out of the charges, and the power represents the energy per amount of time. So that's about it for power. Okay, and that's it for this lesson. Thanks for listening.